exercises and maybe explain a little bit what's going on there. And of course, if you have any questions, please you can look first, for example, the exercise of using subarray data type here. Here's the C version. So I have declared here the sort of block type, the data type for this subblock, and then I need the three arrays basically. I have two-dimensional data array, so the full sizes, what are the subsizes, and the offsets. Then we have the array initialization, and now the data type for the block of matrix. So the full size, that's, we have 8 by 8 matrix. We are using, or we want to sort of communicate part of it. We can put the subsizes here, that it's 2 by 2 subblock we want to communicate. And then the sort of offsets that, okay, start in sort of location 2.3. Then we just create type commit and use that in the communication and print out the result. And if I execute this, compile first. Get this kind of output, so okay, that's the sort of part we get in one of the. We could, of course, very easily make a little bit different size. We could have one of the sizes, for example, here 3. So now it would be 3 by 2 subblock. And if we now run in that print, we can see that, okay, we get now a bit different subblock to this other matrix. And I don't know if anyone you tried to do the heat equation. Here we already had this sort of data types predefined in this data structure here. And we have here some initialization routine for the data types. And here for the data types we want to use for the hello exchange. So this was not sort of size of our original data. We want to add there some boundary data. And this is C code, so for column type we need to make this sort of vector type. And to make the sort of boundary exchange code more transparent, we use this contiguous data type for rows also. So we can, in both send and receive commands, just send single element of row type or either column type. We do the committing. And if you look to actual code how to use that, when we have the data types, just looked at, okay, we want to start from first row. That's the first actual data. first column, send column type, and we want to receive to the last column, which is now the sort of boundary region. We get the data there, similar to the other direction, and also in the sort of up and down direction. So once we have these data types here defined, it's the actual send and receive commands become quite transparent, simple. Otherwise, we would need some manual copying here. And other thing to consider is that we had the boundary condition for the system was that it was not periodic, it was finite. And by using the MPI Cartesian communicator constructs, we could get the neighbors here for each process in such a fashion that if the neighbor was actually, for example, if we have process 0, your leftmost neighbor is nothing, you don't have any neighbor here, you get automatically that this is something like called MPI null, and the actual communication call wouldn't be doing anything. If you would be doing this manually with temporary buffers, you should make sure that also you make the copying only in a case where you actually have some neighbor there. Otherwise, you get incorrect results. We can look also at the data type for sort of parallel I/O here. And this is now for getting the sort of full data to the rank 0 for ASCII printing. In this case, the sort of array where we want to receive, it has dimensions of full NX, full NI, that's the whole amount of data. And in the sending side, in all the other processes, it's actually just the full size is the amount of tail local data, which is just the local dimension and the hello region. Subsizes in both cases, they are the same, so they are the real data, not including the boundary data. And we don't have any offsets here used. And we can create the subarray, and later on in output routine use that one. First rank 0 just copies its own data, and then for each process it can use these MPI card codes to see that which point in the full data array it should receive the data, and then using this subarray data type now, the data will be put in the right position without any manual copying. And here we do the sending for all the other processes. So once again, we are sending the just the real data, not including boundary layers here, which can be done now very easily with this subarray data type. Could look very briefly also at the parallel I/O. That's the probable one we could look. So here we in principle just look what are the amount of actual data for each process and how it corresponds to the full array. So we can use once again these MPI Cartesian coordinate constructs. We open the file and create now file view. So this contains now the sort of size of the whole file, whole array we have. This has these for individual processes amount of, and then what's the sort of each process's location in relation to the full file. And we have Fortran code, it's MPI order Fortran. We commit that. We are not doing any displacement here in file set view, and use this file type constructed of MPI integers, and after that we can just use write and buffer, and this now contains the sort of number of elements of data we have here in terms of integers. In principle, we could use here also our own data type. But I think here it's easier, and this will just now make that okay. The sort of each subblocks, each process has about a 2D full array will go to the correct position in the file. Do you have any questions about user-defined data types or MPI-IO at this point? Okay.
Maybe you can comment about more modern types of working with files and kind of like beyond NetCDF, and what is the norm right now in modern coding. I mean, this is all very basic, and you're coming to see an open source implementation or something, and there are very advanced stuff there. So how can we maybe relate from this to that?
I would say that actually it doesn't go maybe much more advanced if you, for example, think about input and output. Depends a little bit what you want to do with the file. Of course, most real-life applications, at least I work with, they're three-dimensional, so you have to add a bit more dimensions. But I think the underlying idea is still quite the same. So each process has some, especially if you are talking about domain decomposition like codes, each process has their own domain share, and it just wants to get it to the file with so that the file doesn't really depend on the number of processes you are using. It's in the correct order. If it's really data that you also want to analyze, I think MPI is very good for writing restart data and that kind of stuff. But of course, in order to analyze the data, it's a binary data, so you have to probably write your own utility functions to get the data in a form that you can easier analyze. There are these I/O libraries, HDF5, NetCDF, which you can use doing the parallel I/O, and also you can more easily access the data from other software. So I would say that for a real-life application that needs to dump large amount of data that needs also be analyzed, for example, HDF5 might be quite good choice. Basic concepts there are actually quite similar, so you can also sort of define, similar to file views with subarrays, you can sort of hyperslap so that each process writes only to a certain place of file and so on. API is a bit more complicated, so you have to do a little bit more work, but